Let's take a look at an example of a problem we might solve using differentials. So let's estimate the change in the area of a canvas sail in the shape of an isosceles right triangle as the lengths of the legs shrink from 5 meters to 4.9 meters. Alright, that's not a very good triangle, but there's our right angle, and then the two legs are of equal length. And so what's going on is that the canvas sail has been exposed to the elements perhaps, and the sun and the salt and the sea air have all conspired to cause the sail to shrink. But it retains its same shape. So it was originally 5 meters on the side, but then it shrank a little bit. So that's now only measuring 4.9 meters on the side. Alright, so what do we do? Well, note the things that are changing. In this case, we are told that the length of the legs shrinks. So that's changing, and then we're asked to estimate the change in the area. So that's the other thing. Alright, so dA is what we're looking for, if A is the area. And let's call the length of a side, how about L for leg? And so DL is, well, it's either going to be 0.1 or negative 0.1. We'll have to figure out which way we want this to work. Alright, but what you need is an expression that links these two together. What equation can you come up with that gives us the relationship between A and L? Well, this sail is half of a square, so A is 1/2 L squared, right? So let's find the differential now. We take the differential of each side, so the differential of this side is just dA, and the differential of this side would be the derivative times dl, so that would be just L dl. Now, which do we want L to change from 5 to 4.9, or do we want L to change from 4.9 to 5? Well, generally speaking, you want to start at the easier value to work with, and that's typically going to mean an integer, if possible. So I would say that this is the easier value to work with. 5 is easier to work with than 4.9. So let's think of let's think of L as changing from 5 to 4.9. So what that means is that this is going to be 5, and this is going to be negative 0.1. In this case, it really didn't matter. If we had chosen 4.9, we could have gotten a reasonable answer, because we didn't have to do anything with the L. But if we had to, say, square the L, it's easier to square a 5 than it is to square a 4.9. And so that's why you go with the simpler value between these two as sort of the original value, or that's the one you want to use for L, and then the dl has to reflect what happens to L. Alright, so in this case it's the L is measured in meters, and the dl, the change in L, is also measured in meters, and so what we get is negative 0.5 meters squared. So we estimate that the area of the sail changed by about a half a square meter. Now, to find the actual value, you would calculate 1/2 5 squared minus 1/2 4.9 squared, and so that would be delta A. Presumably this delta A is pretty close to dA. Let's take a look at another example. Use differentials to estimate the square root of 48.7. Alright, so in this case what we're going to want to do is to let f of x be the square root function, or x to the 1/2. Maybe I'll write it this way: y equals x to the 1/2. And so we're wanting to approximate what you get when you put 48.7 in. Well, is there a number near 48.7 that would be easy to calculate the square root of? I hope you're thinking the square root of 49. So that's what we're going to do. We're going to think of x as changing from 49 to 48.7. And then y, which is the square root of x, is going to change from 7 to, I don't know. We'll have to figure that out. Okay, so let's let x be the easier of these two values to work with. So in this case, x would be 49, and then delta x, or dx, would be the change in x. So that would be negative 0.3. So then let's go up here and find the differential y. So the differential y is the derivative times dx. That's 1/2 x to the negative 1/2 dx, or 1 over 2 times the square root of x dx. I hope you see now why I was wanting you to choose x to be 49 instead of 48.7. I mean, if we're going to have to calculate the square root of 48.7 down here, then what's the point? So we know that what we're going to do is substitute in the values that were given. So we've got the square root of 49, and dx is negative 0.3. And that's going to be 1 over, the square root of 49 is 7, so 2 times 7 is 14, and then times negative, well, let's see, that's 3/10. So the answer would be negative 3 over 140. Maybe I shouldn't call that the answer. That's dy. But is that, quote, the answer, unquote? What was the question? The question was, use differentials to approximate the square root of 48.7. Well, the square root of 48.7 is not going to be negative 3 over 140. But remember that we said that delta y is f of x plus delta x minus f of x. So delta y is this. That's the exact value, but remember we're using dy to approximate delta y. So dy is approximately x plus delta x minus f of x. Think about what all the x's and delta x's are. So dy is negative. I'm going to come down here and finish this up. Dy is negative 3 over 140, and that's going to be f of 49 plus a negative 0.3. That's going to be f of, or square root of 48.7. Right? F of x is the square root of x minus f of x, square root of x, square root of 49. So 7 minus 3 140ths is approximately equal to the square root of 48.7.